right, so this graph here is a graph of temperature versus heat. So going up and down, we have the temperature of the substance. And then going sideways, we've got the amount of heat Q that we are adding to the substance. And so we're going to start with we're first going to begin with a piece of ice. So over here, we've got a piece of ice, and we're going to start to add heat to it. Okay, and so we are going to get this kind of a slope where the more heat we add, the temperature goes up. And so this part of the graph is given by this formula right here. So you've got the mass of whatever object it is multiplied by the specific heat of whatever that object is, and then the change in its temperature. So going from here to here, you have a certain change in temperature. So from here to here, the temperature changes. That's the temperature change here. And then going from here to here, that would be the amount of heat. So this heat here, and then this temperature change right there. Now, after you've added a certain amount of heat, it's going to start to change its phase or change its state. So this was a solid, and now it's going to do this. So notice what's happening to the temperature. The temperature is not changing because the temperature doesn't change as long as a phase change is occurring. And so now we would use this formula in order to figure out how much heat do we need to add. So this amount of heat from here to here would be given by this formula right here. And it would depend on what is the material, because that's going to be this constant. Okay, then it goes up at a different rate. So notice the slope here is different than the slope over here because it's a different constant. So remember that this one here would use this constant for this material, and then as you're over here, you would go to and you use a different constant for this one. So it'd be a different specific heat constant. Okay, and now notice that the temperature is changing. So now you've got a different change in temperature from here to here, and then that would be the delta T that goes into there. And then you have a certain amount of heat, Q. So this amount of heat right there is going to be this amount of heat. Then the next thing that can happen is it could change from a liquid to a gas. So then it goes sideways because this is going to occur at only one temperature for a certain pressure. So in the case of water, this temperature right here would be 0, and then this temperature up here would be 100 degrees Celsius. And so it goes that way, and then this amount of heat right here would be given by this formula, but you have to use a different C value because this would be the C for changing from a solid to, from a liquid to a gas. And then finally, it goes up again. And so once you continue to add, increase the temperature, the amount of heat it's going to take to do that is going to continue to go up. Now, we could add one more thing to this chart that's not on there. What would that be? So we would need to add one more right here, and then that would be as it's changing from a what to a what? From a gas into a plasma. And then once it's a plasma, then it goes back up again. So then that would be the complete one. But normally we're only concerned about solids, liquids, and gases and not plasmas. But we could graph all of that onto one piece of paper there. So let's look at a sample question here. So we got 100 grams of ice, and the temperature of that ice is negative 10 degrees Celsius. Now we're going to give it 30,000 joules of heat. What is going to happen to it? So our first calculation is we're starting off with a temperature of negative 10, and what do we need to get it to in order to melt it? We've got to get it up to 0. So therefore our change in temperature is going to be 10. So we're going from negative 10 to 0, and that's going to take a certain amount of heat to do that. So the specific heat, we would look that up for ice, a solid. The mass that we're dealing with, now notice that the mass is 0.100 because we had to change from grams to kilograms. And then the change in temperature is 10 degrees Celsius, so 2100 joules. But how much heat did we have to work with? So we had 30,000 joules of heat. So that means that we still have 27,900 joules of heat left over. So what do you think that heat is going to do? Well, that heat is now going to start working on melting the ice. So let's continue here. Next, calculate how much ice can be melted using 27,900 joules of heat. So now we're going to use this equation, and we need to find the constant for water going from a solid to a liquid, and it turns out that there's the constant there. And we're going to solve that equation for m, and it turns out that m is going to be 0.083, and then let's change that back to grams, so it'd be 83 grams. So notice that we did not have enough heat in order to completely melt the ice. So therefore you'll have 17 grams of ice will remain, and you'll have 83 grams of water. So the ice will be floating in the water. Now if we had had more heat than that 27,900, it's possible that we could have completely melted the ice. And then if we had any heat left over after that, then that would have started to cause the temperature to change, and we could have calculated that. So it's time consuming, but if you just take it one step at a time, you can analyze the change of a particular material. All right, let's take a break, and when we come back, we're going to discuss how other variables can control whether something is a solid, a liquid, or a gas.